And we're gonna start in 10, 9, 8, 7, 6, 5.
Good morning, everyone, and thank you for participating in this space weather seminar, of which I have the pleasure of holding the chair for Dr. Mirko Pierzanti, who is a researcher at the National Institute of Astrophysics in Roma, Tor Vergata. And he worked with national and international collaborations for more than 18 years in the field of space weather, and both theoretical and experimental manners. And in 2007, he led the Italian space weather community in the first all-inclusive analysis of geomagnetic storm from the sun to the Earth. And since 2018, he's the Italian scientific director of electrical field and magnetic field data in the Italian Chinese satellite mission CSES Limadu. And for the same mission, he is the scientific director of the MA.I.GIC group since 2020. And in 2020, he also published in Nature the paper of the first lithosphere-atmosphere magnetosphere coupling model during intense seismic activity. Thank you very much, Mirko, for being here with us today, and I will collect and tell you the questions that will be asked in chat. So I leave you the word, and thank you very much.
Thank you, Patrizio. Thank you for the nice presentation. And I want to also thank all the organizers for inviting me. I will start sharing my screen now. Okay. Do you see my screen correctly?
Yes.
Okay, let's start. Today I will talk about one of the most dangerous phenomena that are directly connected with the space weather. What the space weather means? Space weather means all the possible implications that come from the direct interaction between the sun and the Earth environment. In this case, in my presentation, I will show what is called GIC, that it means geomagnetically induced currents, that are one of the most harmful and hazard that is present during a geomagnetic storm. Okay, let's start with a brief introduction on what is the environment and how the sun interacts with the Earth environment. Okay, let's start with the solar wind. The solar wind is a strong flux of plasma, which is essentially protons and electrons that come from the solar corona. The solar wind propagates in every direction from the sun radially at a speed of about 400 kilometers per second. It is not uniform in all its parameters, that it means in speed, density, temperature, and compositions. In fact, they change as a function of the solar latitude. As you know, as everybody knows, the Earth has a magnetic field that can be approximated as a dipole. And it is a very important thing because the Earth magnetic field protects us from the arrival of the solar wind. In fact, the solar wind changed the shape of the geomagnetic field. And in fact, the magnetic field lines that are directed sunward are compressed, while the magnetic field lines that are in the anti-sunward direction are stretched. The plasma carried by the solar wind is forced to flow around the magnetosphere because of what is called the frozen-in theory, that it means that the plasma cannot go inside a magnetic field. In order to to maintain this kind of strange shape of the magnetic field that is very different from what is called as a dipole, the Earth produce electric currents that flow inside both the magnetosphere and in ionosphere. They are the magnetopause current, that is a current that divides directly the magnetic field that comes from the Earth from the magnetic field that comes from the Sun. The ring current that is due to, that is a current that flows in the equatorial plane here, and it is due to the fact that some of particles that come from the Sun precipitate in what is called polar cusp and come inside the Earth magnetosphere and produce this kind of current. Then there is the magnetotail current in form of a neutral sheet that needs to separate the north lobe of the magnetic field from the southern lobe. Then, from a ionospheric point of view, there are two other important currents that are the equatorial electrojet and auroral electrojet, that are currents that flows inside the ionosphere. The ionosphere is the higher part of our atmosphere, and this, differently from the atmosphere that is neutral, the ionosphere is formed by plasma. That means that it is formed by electrons and protons that are splitted and not put together. The solar wind would burn our atmosphere in absence of the magnetic field. In fact, it is always called that we are shielded by our magnetic field from the solar wind. In fact, one of the problems of the absence of the atmosphere, for example, on Mars, that are one of the twin planet of the Earth, is exactly the absence of a strong magnetic field, just like one of the Earth. In fact, thanks to the Earth magnetic field, the solar wind cannot flow inside the magnetosphere and is deflected. Only in particular case events, the solar wind plasma can reach the Earth atmosphere, and in this case, we talk about geomagnetic storms. Geomagnetic storm can produce energy as the Hiroshima atomic bomb of the 1945. They occur when the magnetic field carried by the solar wind is directly southward with respect to the Earth magnetic field that is directed northward, as I show in this figure. In such conditions, the Earth magnetic field reconnects with the interplanetary magnetic field, that is the magnetic field carried by the solar wind, allowing to the solar wind plasma to flow inside the magnetosphere, as I show in this figure. In fact, as you can see here, in case of not reconnection conditions, that are when the interplanetary magnetic field is directly exactly like the Earth magnetic field, the solar wind plasma was deflected, as you can see here, and can flow inside the what is called auroral oval. Okay. Here I show an example, a film of what causes a geomagnetic storm. Here is the Sun in this picture. There is an emission of what is called coronal mass ejection, that is an explosion from the Sun that is directed southward. There is a reconnection, as you can see here, and all the plasma can flow inside the Earth magnetic field. The principle, let me show you again, the principle, one of the principal mechanisms that is driven by this kind of phenomena is the generation of aurora in the northern and southern hemisphere, as you can see here. So now you have understood that the aurora in the northern and southern hemisphere are caused by the plasma coming from the sun that is able to flow inside the magnetosphere. But this kind of phenomena that is like aurora induce a very high and powerful currents in the ionosphere. In fact, the geomagnetic storm can have a serious effect on our technology. In fact, during a geomagnetic storm, you can have a corrosion of pipelines due exactly by what is called geomagnetically induced currents that are inducted at ground due to the presence of currents in the ionosphere. Or GPS scintillation, that it means that because of the presence of great plasma or greater plasma than during quiet times in the ionosphere, you can form plasma bubbles that can deflect the signal coming from the GPS to the GPS receiver. And all the technology directly connected with GPS can fail. Effect, of course, on telecommunications, radiation for civil flights over poles, disruption of national power grids happens in the 1989 when during a very powerful geomagnetic storm, all the Quebec in the Canada have a blackout of 24 hours. And of course, satellites malfunctions and perturbation of radio waves. So, what and why we are studying GIC? As I told you before, the most serious effect on human activity occurring during a geomagnetic storm is induced by a coronal mass ejection. In fact, during a geomagnetic storm, the principal magnetospheric currents that I showed you before and the connected ionospheric currents were intensified, and this caused a rapid change in the geomagnetic field. These variations generates geomagnetically induced current at ground, and they can disrupt the operation of power grids' magnetic survey. In fact, a recent USA government research on the possible economic impact of occurrence of another once-in-a-century severe geomagnetic storm, such as in the 1859 superstorm, shows a potential cost on the national power grid of 1–2 trillion. But what is the physics behind the GIC? The physics behind GIC is related to the Faraday law. It relates the temporal variation of the geomagnetic field to the formation of geoelectric field at ground that drives GIC according to the Ohm's law. It is important to highlight that E depends only on the magnetospheric ionospheric current system and on the Earth geology. Since J, that is the current density, is difficult to evaluate, since the conductivity is a tensor, typically the GIC flowing to a particular network were evaluated. So, in general, we can follow the approach that was developed by Piriola et al. In 2000. The GIC calculation necessitates 2 steps. First of all, the evaluation of a geoelectric field through the evaluation of the magnetospheric ionospheric currents, and of course the knowledge of the conductivity at ground, and the calculation of the flowing GIC through determined geoelectric field and the knowledge of the particular power network. Since the geoelectric field is the primary driver of the GIC, it is therefore the principal quantity that determines the magnitude. Once the geoelectric field is known, it is relatively easy to take the second step, that is the evaluation of the currents, flowing through a power network. In fact, it is very easy to demonstrate that assuming the geoelectric field is spatially constant, the GIC through a power network can be written as the sum of its north-south component in the horizontal plane and its plus its east-west component, always on the horizontal plane. Here, A and B are the network-specific coefficient at each network node and depends on the resistance and geometrical composition of the system. In this case, GICs are measured in ampere. Typically, A and B vary in the range of 0 to 200 ampere kilometer per volt. But what are the open questions here? The principal open question was write down from Pulkkinen in 2019. He, in fact, shows the community that there are three open questions that are related to the GIC. First of all, what solar, wind, magnetosphere, ionosphere proxies are responsible in driving extreme geoelectric field responsible for the GIC? The second one is, what is the relationship between the turbulent feature of the IMF and of the GIC, and which is the mapping of the multiscale in the planetary structures into the ionospheric ones? The third one is how it is possible to forecast the GIC starting from the modeling of the IMF evolution at the Earth in association with the coronal mass ejection. In this scenario, we developed in 2019 the MA.I.GIC model that is the first attempt to give a quantitative answer to the first two questions. So, what MA.I.GIC model is able to do? First of all, MA.I.GIC model means magnetospheric, ionospheric, and geomagnetically induced current model. It is able to, starting from the solar wind observation, evaluate the geoelectric field at ground from magnetic observation at ground, and discriminate between, and of course evaluate, both the magnetospheric and ionospheric origin contribution from ground magnetic observation. Third, it is able to give the first answer to the high frequency variation contribution to the GIC amplitude. How does the MA.I.GIC model work? How we evaluate the geoelectric field? The geoelectric field was evaluated using magnetometer observation and the global ground conductivity model. It is based on this simple equation that is under the assumption of a plane wave propagation vertically downward through a uniform of a lowered medium. Here, we made a direct connection between the geoelectric field and the geomagnetic field through the impedance, but not in the time domain, but in the frequency domain. Here, the geomagnetic field is directly calculated from the observation, and X and Y are respectively the north and east direction. The impedance is directly connected through this equation to the conductivity values, and omega is the frequency. The geoelectric field is simply obtained from the anti-transformation of Fourier. The novelty is that we can evaluate directly the geoelectric field in its vectorial form, starting exactly from the vectorial form of the geomagnetic field. The other thing that is our model is able to do is to discriminate between magnetospheric and ionospheric origin contribution. In order to do that, we applied a new data analysis technique that is called adaptive ALIF, that is adaptive local iterative filtering, that is a method usable for nonlinear and non-stationary signal. In fact, using this method, each kind of signal can be decomposed into a finite number of intrinsic mode component IMCs and a residual of the composition. The IMC component, differently from the Fourier one, are fluctuations over zero, but with an amplitude that depends on time and the frequency that depends on time. So, in this case, the ALIF technique introduced the instantaneous frequency concept. The IMC were ordered by means of their average period. The sets of IMC is local complete in all practical sense. So, how we can directly evaluate the magnetosphere and the ionospheric components. In this case, we used the concept, the idea of Flandrin, that it means that if a clear timescale separation exists in a data set, this can be divided into two different contributions, a baseline and variation around the baseline. The idea is that the variation around the baseline has a close standardized mean and represents the fluctuation contribution of the time series. So we define the variations over the baseline as the reconstruction of a subset of the first k empirical modes, which satisfies the previous two properties, in which here IMC has a close standardized mean 0. Let's now go to an application to the September geomagnetic storm. Here I can show you on the left panels a clear the principal solar wind parameters in terms of solar wind density, speed, temperature, interplanetary magnetic field, the three
Scusami Mirko, sei muto. C'era un'altra persona con il microfono aperto e probabilmente ho messo in muto lui e sei andato in muto anche tu, scusami.
Mi sentite adesso?
Adesso sì, grazie, scusami.
Ok, perfetto, no problem. Ok. As I show here we show the principal solar wind parameters during the arrival of the interplanetary coronal mass ejection that causes the geomagnetic storm of September 2017 in terms of solar wind density, speed, temperature, interplanetary magnetic field, the three components of the interplanetary magnetic field, and two indices that are the CMEs and the A index that are representative of the geomagnetic activity at lower and higher latitudes. As you can see here from the two dashed lines, there are two interplanetary shocks that are identified in all interplanetary parameters. Then there is the arrival of the ICME in terms of magnetic cloud. In fact, there is an enhancement of the IMF strength and the smooth rotation of the BZ IMF. Then there is the arrival of the second shock, and after a sheet region, there is the arrival of the second magnetic cloud. So you can see here that the September 2017 geomagnetic storm was characterized by two CMEs, the arrival of two structures of the Sun, the first one and the second one. What is the ground response to the arrival of these two kinds of structure? As you can see here at low and higher latitudes, you can see here that the geomagnetic field fall down abruptly in the first arrival of the first on the arrival of the first interplanetary coronal mass ejection and the arrival of the second coronal mass ejection. Here we report the north-south component of the geomagnetic field and east-west component of the geomagnetic field. This kind of behavior is very similar to what is happening at very higher latitudes, where due to the action of the auroral electric jet, the decrease of the geomagnetic field is higher, very higher with respect to what happens at very low latitudes. So, using Aleph, we decomposed both the north-south and east-west component, and we obtained 21 IMC. Applying the Flandrian property, we defined the magnetospheric contribution, the ionospheric contribution, and the high-frequency contribution. That means the turbulent character of the response to the arrival of the IMC. So, as expected, at low latitude, the magnetospheric contribution here is dominant with respect to the ionospheric contribution, because there is a lack of the auroral electric jet. While at higher latitude, here is the magnetospheric contribution, and you can see here that the ionospheric contribution is dominant, and it is due to the action of the auroral electric jet. The same happens to the D component. So, what happens if we evaluate the GIC? The GIC along the east-west component and the north-south component are evaluated by our model, and you can see here in the upper panel and in the lower panel. The same is at higher latitude along the east-west component and north-south component. But what guarantee do we have to evaluate the correct geoelectric field? What we would need is a direct comparison with geoelectric field observation at the same location of the geomagnetic ones. Okay? But we can do that because we can compare with geoelectric field measurement from magnetotelluric observations. That it means, let's have a direct comparison with real geoelectric field observation. And here we show now the direct comparison with Boulder, Kakioka, and Kanoya magnetotelluric observatories. And these stations, in fact, contemporarily measure both the geoelectric field and the geomagnetic field. You can see here a direct comparison between Boulder, east, west, and north-south geoelectric field that are measured in blue and derived from a MA.I.GIC model in red. You can see here, and it also confirmed by the scatter plot, that the correspondence is very good. The same happens for Kakioka. Also in this case, this comparison is very good. The same is from Kanoya. In this case also, the comparison is very good, despite there are, in this case, some points in which our model is not able to correctly evaluate the geoelectric field measurement. So, since we are able to correctly depict what is happening at each location where we have a geomagnetic observatory, we have a dream. Can we have a global picture of the GIC hazard when we have something that is coming from the sun? Yes, we can. In fact, we can use, for example, here, 74 ground stations that measure the geomagnetic field, and what we obtain is a global map of the GIC hazard relative to the September geomagnetic storm. What we obtain is a global view for the first sudden impulse, for the first main phase, and for the second main phase. As expected, the higher GIC values are at higher latitudes because, as I showed you before, there is the action of the auroral electrojet. That is the greatest currents, the highest current that flows in the ionosphere. But we can do better. We can make a movie. So I show you here a movie of what is happening during the arrival of the geomagnetic storm. Let's show you again. Here is the arrival of the first shock, and you can see here the greatest values of the GIC for the first sudden impulse, for the first main phase, here, boom, arrival of the interplanetary coronal mass ejection, and for the second main phase in Europe. Boom, here is the arrival of the second main phase. Interestingly, I will show you a picture here. Here is the Italy, here is the northern Italy. As you can see here, this kind of very huge value of the geoelectric field can influence also our power network. So in conclusion, we evaluated in a new way the GIC over the Northern Hemisphere during the September 2017 geomagnetic storm. We introduced a new model able to evaluate a realistic measure of the electric field induced during high disturbance conditions for the first time. Our model was able to efficiently discriminate between the ionospheric and magnetospheric field contribution involved into the GIC calculation. This is the first observation of the direct relation between the highest value of the GIC and the ionospheric induction process. The GIC calculus has been conducted for both the September 2017 standard events and for the entire main phases of the relative geomagnetic storm. And the knowledge of both the magnetospheric and the ionospheric current behavior during and possibly before a solar event is very important in modeling and prevent any damage induced by the GIC. The MA.I.GIC model represents the first attempt to produce a global view of the magnetosphere-ionosphere system. Thank you for your attention. That's all for me.
Thank you. Thank you very much, Mirko, for your very, very interesting seminar. It's absolutely astonishing how the sun will determine our lives, even not only for the warmth or for the light, but even for his coronal activity. And very, very interesting. Thank you very much. I'm going to read you a question from the chat.
Yes.
It is from Marco wrote this, so I don't know if it's from Marco Casolino. I can read. Marco Casolino say ciao Mirko. I don't know if the question is also from Marco. Anyway, the question is a generic question. Can CMEs be observed to predict along with your model when and where GS will happen, and maybe even to exploit them, for example, energy generation? The question is from Marco. So
yes.
Marco Bonzetti.
Thank you, Marco, for your question. It is a very important question. Yes, our model can be used to try to predict the GIC over a global scale, as I show you during my presentation, what we need in this case is a model of the coronal mass ejection behavior. That it means how the coronal mass ejection and when the coronal mass ejection will impact onto the magnetosphere. In our case, what we do is something like nowcasting process. That it means that we can use solar wind parameters that are observed at the first Lagrangian point, that is at around 200 Earth radii distant from the Earth, and typically a coronal mass ejection needs 30 minutes to arrive to the Earth. And in using this time delay, we can, in this case, use the parameter to forecast the GIC. But in order to have 1 or 2 days forecast, we need a model of the coronal mass ejection behavior in terms of, for example, coronal mass ejection speed, density, temperature, and interplanetary magnetic field.
Very interesting. And I'm also thinking about the fact that it could, Marco is asking, Marco thanks you, and he's also asking about energy generation. This is a curiosity from me. Do you think it is possible to use this incredible energy mass to be exploited for human usage?
I don't know. I don't know. It could be, because when you have this kind of current that is flowing at ground, in principle, you can try to put them in a box. Let me pass the term, and try to reuse it. But probably the how does it means the time scale, the duration of these currents are probably too little in order to be used by the human activity, but the time scale are exactly are perfect in order to produce very high damage to the national power grids. In fact, of course, in fact, in the 1989, there was the famous Halloween superstorm. Some of the principal Quebec transformers were completely burned out.
Yes.
From the injection of those GIC.
So I hope we will try to find a way to use this energy. It could be part of the solar energy exploitation. And there is another question from Simone Rossoni. Hi Mirko, does the presence of the moon affect the arrival of such storms on Earth?
Yes or not? Okay. The moon, of course, have an orbit that is out of the magnetosphere in the dayside region. That it means the region that is look at the sun, and is inside the magnetosphere in the anti-sunward direction. So since the Earth, in my knowledge, have not a magnetic field, a proper magnetic field, I think that cannot prevent the arrival of the GIC. But when there is something like an eclipse, it can produce a change in the local ionospheric conductivity because of the miss of the photoionization, and it could lead probably to a decrease of the ionospheric currents and hence a decrease of the relative geomagnetically induced currents.
So even with the mass of the moon, it's transparent to those magnetics.
Yes,
even with the enormous mass of the moon.
Yes, because what is important here is the magnetic field. The only thing that can shield from the passage of particle coming from the sun is the magnetic field.
So there is another curiosity from Marco Ponzetti. There is proof that electromagnetic field inverts every few 100,000 years. And could this inversion have a predisposition effect for GICs, at least in theory?
Yes, very interesting question. I want to tell Marco that it is an open question, an open problem, because in the human history, there was any kind of flip of the geomagnetic field. Probably there are some studies that tells that probably the possibility of the human life to have this kind of prosperous behavior is due to the fact that we have a very prolonged and stable geomagnetic field. But in the last 3 or 4 years, the geomagnetic poles are moving faster, and we are probably going through possible flip of the geomagnetic field. So I think that there are models that show that the magnetic field needs 20, 30, 100 years to come back to its, let me pass the comfort zone, let me pass the word. There are many others papers that show that the flip has a time scale of minutes, and so probably we did not observe any kind of changes. But they are models, and many times models are very different from the reality. So the problem is very interesting, but it is an open question.
Okay, so this is for me, this is not only a problem of flipping, it's also a problem of moving, because there is probably a complete flip could be easily balanced by electronic devices or software models, but moving from a position could be even difficult to predict, to model, or to compensate with electronics or software. There is Simone Rossoni says, thank you for the answer and for the presentation. He also hopes to see you soon.
Okay.
Simone Rossoni. If there are other questions, there is one from Giuseppina Carnevale. Hi Mirko, what are the rules played by ionospheric turbulence in amplifying GICs?
Thank you for the question. Very important question also in this case. Since the geoelectric field is due in principle by the Faraday law, that it means that is directly connected to the variation, to the derivative of the geomagnetic field. Of course, the more the geomagnetic field change rapidly, the more you have an amplification of GIC. So probably the turbulence play the key role in amplifying the amplitude of the geoelectric field and hence on the currents. So in principle, if you have a stable, as I can say, okay, a stable ionosphere, you have a value of a current I. And if you have a turbulent ionosphere, probably you have a higher value of 25%. Very high.
Okay. So I think Giuseppina is satisfied with your reply. And I can see no other questions in Teams chat, and I'm asking Marco if there are questions from the YouTube channel. Okay, Giuseppina.
No, from YouTube.
Perfect. So Giuseppina say thank you, Mirko.
Welcome.
And I think if we have exhausted all the questions, I can pass the word to Marco for saying goodbye for this for today. Thank you, Mirko. Thank you very much for this seminar, and thank you, Marco. Thank you, Marco, and I pass the word to you. Thank you.
Yeah, thank you both, Mirko and Patrizio. So it was a very interesting seminar. So I think everyone was very intrigued by the topic. It's yeah, thank you very much. Yeah, I just want to say that next week we have a pretty steep change of topic, because we will talk about archaeology and the new technologies used to study some archaeological events in let's say with a professor from UNIVAC. So I'll see you next week on these teams, and I hope to see you there.
Okay. Thank you very much. And I want just say a few words to conclude that every student that wants to have more information or wants to help me in understanding GIC or wants to try to put their attention on space weather can contact me directly. They can ask Patrizio my email, or okay. Please share it, and I will also give you my presentation. And if there are some people that want to have my presentation, you can give it. Okay.
Thank you very much. Thank you, Marco. Thank you, Mirko. Thank you, Marco. And bye bye. Thank you.
Thank you, everyone.
Bye bye. Thank you.